Hello, my name is Gokul, and today I'll be presenting my work, Privadome, Delivery Drones and Citizen Privacy. This is joint work done with Ajit, Ekansh, and Professors Vinod and Arpita. In recent years, we've seen a rise in the number of drones that are being used. End user drones are now commonly available, and not only are they available, they're equipped with sensors such as cameras and GPS. These pose a major threat to individual privacy. On top of that, regulations are loose and mechanisms to enforce privacy are lacking. In this work, we focus on delivery drones. Now, why delivery drones, one might ask? The main reason being is that incentive to comply with privacy regulations are much higher for delivery drones. These are usually run by e-commerce companies with reputations to protect, implying they don't have any overt malicious intentions, which makes it easier for a threat model to exclude rogue drones. They also have a strong interest to comply with local regulations in the first place. Yet, despite all these reasons why drones might or should take off, privacy remains a problem. For example, drone-based coffee trials by Alphabet led to protest and a parliamentary report for oversight on their privacy implications. Laws have been suggested to ensure data gatherers incorporate suitable accountability mechanisms to protect citizen privacy. Enter Privadome. Privadome aims to implement the vision of a quote-unquote virtual privacy dome centered around the citizen. Privadome detects drones that may be in a citizen's vicinity and determines whether that citizen is captured in the field of view of the drone's camera. It also provides suitable mechanisms for the citizen to determine whether the pictures or video captured by the drone preserve the citizen's privacy or not. Where does Privadome fit? Designed to be integrated with a city-scale regulatory authority that oversees delivery drone operations. It works on the premise that regulatory authority is aware of the identity and current location of delivery drones operating in the city. Such requirements have been posed in drone laws of various countries, and it's not a far-fetched assumption to work with. What are the components of Privadome? We need to allow citizens to find delivery drones whose cameras have them in the field of view. Enter PDMPC, which makes use of secure multi-party computation to accomplish this goal without compromising citizen location. Once such a list of drones is present, the drone must convince the citizen that their privacy is maintained. Enter PDROS, an exemplar framework built on ROS2 based drones, which audits data flows between applications within the drone and offers proof via trusted hardware. Here is an outline of what our Privadome system looks like and how it might be implemented. As step 1, drones register with regulatory authority that oversee their operation, providing their location to them. As step 2, a citizen who wants to protect their privacy queries the regulatory authority with their location via PDMPC and obtains a short list of drones. Now, the regulatory authority and the privacy cognizant citizen engage in an MPC protocol, the output of which is a short list of drones. Step 3, the citizen obtains audit trails from drones via PDROS to check for privacy violations. This is the complete deployment vision of Privadome. Now, the threat model is such that the main goal is to protect citizen privacy. Therefore, the threat model is citizen-centric. The regulatory authority is trusted, but the citizens do not have to reveal their location. We expect companies to run drones with trusted hardware, which is supported by legislation as well. It also excludes drones which are not registered with the regulatory authority. Now, how do we shortlist drones via PDMPC? PDMPC is a system based on two-party MPC involving a citizen and the regulatory authority. At the end, the citizen has a list of drones which have caught him in their field of view. The question then becomes, how do you identify interesting drones? As depicted in the image, the capture of interesting drones is done via a calculation that involves the citizen's location, the drone's location, its direction of motion, as well as its field of view. Using these parameters, we can come up with a simple algorithm that captures all the users that were present in the drone's field of view. Here, the drone's field of view can be obtained from its build, which is known to the regulatory authority. This is the algorithm formally codified. Dist here refers to the Euclidean distance between the 2 points which has to be calculated. The procedure vectorize actually uses equirectangular projection, where we have to convert from GPS to a flat plane in order to find the required vectors. This algorithm also makes some assumptions where it only considers the horizontal field of view, as well as the fact that it assumes the presence of a forward-facing front-mounted camera. However, the algorithm can be modified accordingly to apply a corrective factor in case of multiple cameras or a vertical-facing camera, which would mitigate the problem. However, the straightforward algorithm requires to be modified in some aspects, namely security and performance, for it to work. For example, we cannot reveal the result of the computation to the regulatory authority to avoid side channels. It could use the Boolean result to determine the set of drones near the citizen. MPC protocols allow us to do that, and we leverage that. Modifying for performance as well. Distance computation is heavy in nature. Standard formulas, for example, Haversine, Vincenti's, are accurate but impractical. Instead, we approximate by using differences between latitude and longitude to calculate the rough distance. It allows us to reduce the cost of a particular distance calculation from around 180 kb to 0.3 kb per query. Therefore, this is what the MPC setup in Privadome looks like, where, as you can see, there is an example of modification for performance as well as a modification for security. Now, when it comes to implementation, we use Motion, an MPC framework based on secret sharing protocols to implement the above algorithm. Results indicate that our secret sharing based implementation scales to hundreds of drones at city scale. Practicality of Privadome at city scale is something that we always wanted to keep in mind. Therefore, as you can see, for 1000 drones in the air at any time in the city, the amount of data consumed per query comes to around 6.59 MB. We feel that this is a reasonable estimate for a near-term deployment, and with improvements in MPC protocols, the number will only further come down. Here, we also see that the latency per query. For 1000 drones, the latency is roughly 16 seconds, which again we feel is a reasonable amount of delay, given the fact that the user won't necessarily query for this frequently. Now, let us talk about auditing compliance with the help of PDROS. With the shortlist of drones, Citizen uses PDROS to obtain audit trails from drones and ensure that they are privacy compliant. The goals are twofold. We need to ensure that we only use sanitized data. Therefore, PDROS must ensure that the camera data is never used unsanitized. It must also offer compliance proof. Therefore, it must be able to convince citizen that the above goal is satisfied. To reliably offer proofs of compliance, PDROS assumes the presence of trusted hardware on the drone. The hardware must be capable of performing basic cryptographic operations, offer the ability to securely store an audit trail, and respond to citizen requests with a digitally signed audit trail. A short aside on ROS2. ROS2 is a popular middleware platform for robotics which uses the PubSub model. It consists of a set of libraries and user space utilities for development of applications. Vanilla ROS2 is not secure, therefore the community has developed SROS2. PDROS builds upon ROS2 extended with SROS. In SROS, TLS is used to secure the communication between applications. Further, each application must provide a manifest that declares the list of topics to which that application publishes or subscribes. The application's code and this manifest are then cryptographically bound via an X.509 certificate signed by a trusted third party. Now, let us look at PDROS's operation. Step 1. Instead of video feed, applications subscribe to a Priv video feed, ensuring that they always receive sanitized video. No app is allowed to consume video from the camera directly. Step 2. Trusted Video Sanitizer runs in the secure world, where it receives raw video, applies a filter, for example blurring, and sends the sanitized feed back to the normal world. In step 3, the ROS2 app launcher is modified to send the SROS manifest, which contains details about which application is subscribed to which topics to the secure world whenever an application is launched. This manifest forms part of the proof whenever the user requests an audit trail. Now, evaluation of PDROS was implemented on an NVIDIA Xavier NX development kit. The numbers were obtained by sending 250 frames at 30 frames per second. As you can see, the overhead in terms of time taken is minuscule, with the major cost coming from the CPU utilization and power consumption. Further optimizations to PDMPC, where recent advances show that several steps of the OT can be computed as a pre-computation step, further reducing online mobile data computations. Several frameworks also are optimized for mixing Boolean and arithmetic computations, making switching between these worlds efficient. Therefore, we conclude with the fact that Privadome is a framework that can be integrated with city-scale regulatory authorities to oversee drone operations. It allows citizens to query for privacy violations. It accomplishes all this without revealing citizen location, modest data consumption, and low runtime overhead. Thank you.